Yes, welcome to the presentation from my side. I will present you a new stage-based reduction approach in the context of satisficing classical planning. That means we have a planning task with variables, assignments of variables, which is a state, an initial state, and a goal, and a set of operators. The aim is to find a plan from the initial state to the goal with the given operators, and the plan doesn't need to be optimal in the context of satisficing planning. My presentation focuses mainly on the set of operators because we can observe that planning tasks often contain significantly more operators than needed for a plan. Here we have a table with some examples where we see the available operators in a planning task. These are counted operators, and the amount of operators which occur in a plan. For all instances which were solved in a run, there are 4.3% of the available operators which are needed for the plan, which is a low number. So we can ask the question, how can we exploit this observation? Of course, we can reduce the set of available operators. Planning task with such a reduced set we call under-approximation. But what if the planning task turns unsolvable? You can assume a planning task where with a operator set that is empty, and such planning task is obviously unsolvable because we have the initial state, a goal, but no operators to reach the goal. So what can we do? We can add some operators to the reduced set, which we call refinement. We can do iteratively as long as we find the goal. I explain it in more detail with this diagram. We have the original planning task, and we select an initial operator subset to get the first under-approximated planning task. Then we run a planning algorithm on this first under-approximated task, and if the judge finds the plan, we can return it. Otherwise, the refinement guard will trigger at some time, and we can refine the operator set of the current under-approximation. If the refinement delivers new operators, we must update the search by reopening closed nodes where new operators are applicable. Afterwards, we continue to search on this new under-approximation, on this refined under-approximation, until a plan is found, and if not, we iteratively do refinements. This this under-approximation refinement algorithm has several parameters. You can choose the planning algorithm. You can choose the initial operator subset. You can ask how and when do we have refinement with the refinement guard, and which operators do we want to add in a refinement. Yes, we created a first instantiation for these parameters, and this instantiation is based on real explains of the FF heuristic. For the planning algorithm, we use 3D-based word search with the FF heuristic, and the heuristic is evaluated according to the concrete task, to the original task, because if we would evaluate it on the under-approximated task, the heuristic would be uninformed or return too many dead ends. As an initial operator subset, we simply use the operators from the relaxed plan starting in the initial state. And the refinement guard triggers if the open list is empty, that means the under-approximation plane task is fully explored. Then we need to add new operators, or we are on a plateau or on a local minimum. Yes, and the refinement, which asks which operator we want to add into the under-approximated plane task. Here we consider the closed list, and we order the state in the closed list according to their heuristic values. Then we select the state with the lowest heuristic value and create the relaxed plan on these states, because these states are assumed to be the nearest to the goal. That when we have created the relaxed plans, we select the operators, and these operators will refine the current under-approximation. If no operators can be found in these best states, we scan the closed list and try to find operators, new operators in the relaxed plans. Yes, of course we want to preserve completeness. If we would only use relaxed plans or operators from relaxed plans, we wouldn't be complete, because relaxed plans are not sufficient, not in all problem instances are not sufficient to find a goal. Therefore, we add applicable operators when the under-approximated task is fully explored, and when the relaxed plan doesn't deliver new operators. Now I come to the evaluation. We implemented the under-approximation refinement framework into the path downward planning system. Then we evaluated our first proposed instantiation, and in addition, we also evaluated two further instantiation, which simply has author planning algorithms, namely the preferred operator and the look-ahead strategy from ICAPS 2. Yes, and in the evaluation, we compare the planning algorithm with the same algorithm run on under-approximations. So in this table, we see here in brackets the amount of available operators in the last under-approximation. It's the percentage of all available operators, but only this one in the last under-approximation. Yes, we see that we can significantly reduce the amount of operators, and yes, we have improvement in the coverage, especially for the Baumann domain and for the optical telegraph domain. And at the woodworking domain, it doesn't perform so well. I will give some reasons later. And this table only shows the instances where one configuration served at least two instances more than the other configuration. Now I show you the plot where we see the coverages at specific time points. On the top we have the first instantiation. We see that even in the first second, the under-approximation refinement approach has a higher coverage. Also when we search with preferred operators, and even with JASP 2, but only in the beginning. Later we see the plain JASP 2 search is better, but this is mainly due to the woodworking domain, which performs similar with on under-approximation. Now a few remarks. The upside of this approach is that we reduce the set of operators and for branching factor. And this seemed to be good for optical telegraph and Bowman. I need to say that it may depend strongly on the instantiation you choose, but maybe we can say generally for judging on under-approximations. The downside is that the judge may spend too much time in an under-approximation due to missing operators. And yes, the required operators may be added unfortunately later in the judge. We assume that this is the case for the woodworking domain. Now I come to the conclusion. We can improve existing arbitrary existing satisficing planning algorithm with under-approximation refinement. We didn't test all the algorithms, but it should be easily adaptable. Then our first instantiation is already competitive with the state of the art. However, the under-approximation refinement with the different parameters allows for more powerful refinement strategies. And we would be glad for some ideas how to create for more instantiations of these parameters. Thank you for your attention.
Christian.
Yeah, so I really like the first table where it showed such a reduction in the number of operators you actually need for some of these problems. And it really reminds me that it'd be really good to start moving towards solving problems where we don't ground everything out and then try and solve it afterwards. Have you thought of how you might try your under-approximation before you start grounding? So only ground the operators you think you might need, and then refine your approximation by grounding more operators afterwards.
Sorry, I didn't understand.
So, correct me if I'm wrong, but you ground all of the operators that you need, and then you select a subset, and you try to plan with those. So have you thought of not grounding everything? So some domains, there's too many operators to ground, but just selectively grounding the operators you think you might need, and then your refinement step would ground more operators?
That would be a good idea. We didn't test it, but yes, we considered only grounded operators.
Because I think you'd have a lot of potential in some of these domains and some of these problems with just way too many operators to ground.
Yes,
it could be really helpful.
That would be another kind of refinement, of course.
Jörg.
I might have a suggestion for a different initialization, like different action set for the start. So if you just collect the actions on a relaxed plan, a common pattern is that, well, the plan only needs to move outwards from its initial start, the relaxed plan. Like it has a tree through the DGG, okay? It just goes from a start value to all values that are needed. Now, if you just include the backwards action or some tour through the values it needs to visit, it might be useful. I'm not sure how often it occurs in the domains you're testing here, but it's an idea I would try anyway.
Thank you.
Any other questions? All right, so let's thank the speaker. So our next speaker is Jörg Hoffmann.